In this video, we will go over core concepts and the configuration steps necessary to get your game working with S.A.M, also known as the Streamable Assets Manager. This video will not be an in-depth dive into all aspects of S.A.M, as S.A.M is a complex package with too many features to cover in detail in a single video. Instead, we invite you to explore our other tutorial videos covering specific topics in detail, which we will mention and provide links for when appropriate in this video. It's also important to note that this tutorial video closely matches the Getting Started tutorial chapter found within the In-Editor guide, so if you're a S.A.M user that has already worked through that chapter of the guide, this video will be somewhat redundant. Our journey begins from the ground up, starting with the most basic of concepts and building blocks. From these building blocks, we will work towards understanding more complicated concepts while slowly building an arsenal of assets, game objects, and components that will eventually resolve into a working game world. To start, let's talk about assets. Assets are typically individual game objects that represent objects in your game world. However, it is possible to use non-game object assets in S.A.M, though doing so requires custom scripting. In this example scene, each tree is an asset made of two assets, a trunk and leaves. The terrain piece is also a separate asset. In S.A.M, assets cannot always be loaded directly. They must be converted or grouped together into streamable asset chunks, which are the base units that can be loaded, unloaded, and manipulated by S.A.M. Streamable asset chunks are the fundamental building blocks used by S.A.M to construct game worlds. While assets are usually game objects, asset chunks are typically prefabs or game objects stored as the root parent of a containing scene. You can see an example of both types of asset chunks here. Our terrain is a prefab, while our tree assets have been grouped together under a single root parent, which serves as the asset chunk. That chunk is contained in a scene, which serves as a vehicle for streaming the asset chunk into the active scene. While technically the scene is just a vehicle and not the actual asset chunk, it is usually best to consider it as the asset chunk up until the time that it is loaded. In many cases, an asset chunk will only consist of a single asset, and in these cases, the underlying asset and asset chunk are synonymous. We can see asset chunks like this in our scene by viewing our terrain. As you can see, each terrain is simply a single prefab without any children. In other cases, an asset chunk may consist of tens, hundreds, or even thousands of assets. For example, you can see in our scene that we have a small forest made of trees. Rather than loading each of these trees individually, the trees have been grouped together under a single asset chunk, which allows us to stream them in with a single loading call. A streamable cell represents a defined square or cubical space within the game world and is associated with one or more streamable asset chunks. The chunks do not necessarily need to fit neatly inside of the cell, however, typically they will. When the Streamable Asset Manager loads assets, it does so by putting in a call to load a specific streamable cell for a specific LOD. All streamable asset chunks associated with the LOD of that cell are then loaded in. For some asset types, a cell will only ever have one asset chunk, such as when using Unity terrain. Multiple chunks are advantageous when your game is unable to load a single chunk in a performant manner. For example, take the forest we see here. It contains 24 trees, which will probably not affect performance too much if loaded in using a single load call. However, if the forest contained hundreds or thousands of trees, we would probably need to divide those trees into separate load calls. To do this with S.A.M, we would just need to create additional asset chunks, which you can see us doing here. Now, when I load this streamable cell, each asset chunk is loaded in a separate load operation, each of which will have less of an impact on performance than the original single asset chunk. Although these asset chunks are separate objects, internally they are grouped together within a parent world cell object and are manipulated as one. Streamable cells are grouped together into one of the most important assets in S.A.M, the streamable grid. The streamable grid is a scriptable asset that stores important information about streamable cells and their associated asset chunks, information which is used by S.A.M to build the game world. You should create your first streamable grid now by right-clicking the folder where you wish to create it and selecting Create. Deep Space Labs, S.A.M, Streamable Grid. By default, the asset is given the name Streamable Grid. However, you should rename it to better reflect the asset chunks the grid is intended to represent. For example, this first grid will be used to represent my terrain, so I will rename it to Terrain Grid. Renaming the grid will help you differentiate it with other streamable grids, which will make identifying the grid later much easier. The axes option controls which axes streamable cells are placed on, which axes are tracked when using active grids, which axes are recentered when using origin recentering, as well as whether streamable asset chunks need to include a layer value in their names. There are 3 options. With the 3-dimensional option, your streamable grid can have multiple columns, rows, and layers of cells on the X, Z, and Y axes respectively. Additionally, the player's X, Y, and Z position can be tracked in order to determine which of these cells needs to be loaded at any given time. With 2-dimensional using X-Z axes, the grid can only have a single layer of cells, and every cell will have the same Y position. The grid can, however, still have multiple columns and rows on the X and Z axes. Only the player's X and Z position can be tracked to determine which cells should be loaded. The Y value of the player is ignored for both tracking and world recentering. Finally, with the 2-dimensional using X-Y axes, the grid can only have a single layer of cells. However, this time, the layer is placed on the Z axis, which means all cells will have the same Z position. Again, the grid can have multiple columns and rows, but they will be placed on the X and Y axes, respectively, and only the player's X and Y position can be tracked to determine which cells should be loaded. The Z value of the player is ignored for tracking and world recentering. In general, we recommend using the 3-dimensional option as it allows for the most flexibility in expanding your world across all 3 axes. However, if you are certain that you only want the player's position to be tracked across 2 axes, you can elect for one of the 2D options. Also keep in mind that 3-dimensional grids can be used in conjunction with 2-dimensional XZ grids with some limitations, so you do not necessarily need to choose the same axes type for all the streamable grids on your world. When determining axes for existing asset chunk groups, choosing the axes type is relatively straightforward. Take this group of terrain, for instance, which has been produced using our other product, Terra Slicer. If we examine the positions of the terrain, we can easily see that a set of columns and rows have been formed that vary across the X and Z axis respectively, while the Y position of each terrain is the same. Thus, 2-dimensional using XZ axes is the natural choice. However, it should be noted that terrain and other ground meshes can be used with 3-dimensional axes, and in fact, doing so is recommended in certain situations, as it opens up the 3rd axis for dynamic streaming, which can help add a sense of verticality to your game. It can also be used to create cool worlds such as one full of floating islands. In order to use these terrains with a 3-dimensional grid, however, we would need to rename them or reslice our source terrain to include a layer number. So for this video, we will stick with the 2-dimensional option for simplicity, with our rows making use of the Z-axis and columns the X. Remember, using this axes type means that it does not matter if I move the player below the terrain or far above it on the Y-axis, as that axis cannot be tracked. It is only the X and Z position that will be tracked and used to determine what should be loaded. As stated previously, each streamable grid is made up of rows, columns, and layers of streamable cells. The number of rows, columns, and layers you use is entirely up to you, with 2 restrictions. First, as stated before, only a single layer can be used with 2-dimensional axes, which means in this example we cannot adjust the layer value. Second, when using multiple streamable grids on the same world, each grid may have a differing number of rows, columns, and layers. However, the total size of each grid on each used axes must be equal. For example, take the grid that will be used with these terrain. Each terrain has a width and length of 125, and there are 8 rows and 8 columns. This results in a total width on the X-axis and length on the Z-axis of 1,000. Other streamable grids that are used on the same world as this terrain grid can use a different number of rows and columns that have widths and/or lengths different than 125. However, the total width and length of all combined columns and rows on those grids must still equal 1,000. Sometimes choosing the number of rows, columns, and layers is easy, as we already have asset chunks that tell us these values. In this scene, for example, we have 8 rows and 8 columns of terrain, whose sizes exactly match our streamable cells. Thus, we can use the same number of rows and columns for our terrain grid. We can change the number of rows and columns on our terrain grid by setting the new values in the appropriate fields. Doing so will do nothing on its own, however, as can be seen in the values in parentheses, which tell you the true current number of rows, columns, and layers in use. In order to commit the changes, it's necessary to press one of the 2 update buttons. The update buttons are required because changing the axis sizes can both be an expensive operation as well as result in a loss of data. The only difference between the two buttons is the state that new cells will be set to, and as such, there is no difference between the two when solely reducing the number of rows, columns, or layers. If you are unsure of which state to set new cells to, or are planning on creating streamable asset chunks using the World Designer tool at a later time, it's best to start with New Cells Disabled, which can be accomplished using the Update Disable New Cells button. If you are certain that all new cells should be enabled, however, you can use the Update Enable New Cells button instead. In this example, we will be utilizing all of the streamable cells in the grid, so we want all the new cells we add to be enabled by default. The visual grid that sits below the update buttons serves several purposes. Because cell dimensions are defined by the individual row, column, and layer dimensions, all cells on the same row will have the same length, all cells on the same column will have the same width, and all cells on the same layer will have the same height. You can enable cells which are currently disabled by left-clicking them, and disable cells that are currently enabled by right-clicking them. The visual grid only shows up to 4 rows and columns of cells at a time. However, you can scroll through the rows and columns using the scroll wheels above and to the right of the grid. Because of this limitation, however, when working with larger streamable grids, it can make more sense to use the World Designer tool to enable and disable cells. If using a 3-dimensional streamable grid, you can also scroll through the layers using the slider above the visual grid. The visual grid also shows you the dimensions of each row, column, and layer on your streamable grid, which can be seen within the parentheses for each row, column, or layer. Each column on a streamable grid can have a unique width, each row a unique length, and each layer a unique height, though in general it is unusual to have a grid use different column widths, row lengths, and/or layer heights. Because cell dimensions are defined by the individual row, column, and layer dimensions, all cells on the same column will have the same width, all cells on the same row will have the same length, and all cells on the same layer will have the same height. When determining the dimensions of asset chunks which completely fill the streamable cells, as our terrain do here, choosing the dimensions is very easy. We need only look at the dimensions of the terrain themselves, which we have already determined to be 125 for both the width and length. We can configure the dimensions of individual rows, columns, and layers by clicking the button associated with the row, column, or layer, entering a value in the modal window that is displayed, and pressing Enter or clicking Apply Changes. In this example, however, we want all rows and columns to be set to the same value, so we can use the buttons that surround the visual grid instead. These buttons correspond to a group of cells which will be affected by the operation. Clicking all rows, for instance, will open a modal window that allows us to set the dimension of all rows to a single value. Here, we are using the Everything button to set every row, column, and layer to the same value. In reality, our terrain height is not 125, it is 208. While it is not required to configure the layer height to be equal to the terrain height, doing so is usually a good idea. We can make that change by clicking on the L1 button and entering 208 in the window that is shown. For 3-dimensional grids, this layer button will change depending on which layer you are currently viewing. One final thing to note on the visual grid. In addition to using the row, column, and layer buttons, as well as the all rows, all columns, and everything buttons to set the dimensions of rows, columns, and layers, you can use these buttons to batch enable or disable multiple cells at the same time. To do so, hold down the Shift key and left-click to enable a group of cells, or hold Shift and right-click to disable them. The group of cells that is affected depends on the button that you press. For instance, we can disable all cells in column 3 by holding Shift and right-clicking the C3 button. Of course, in this example, we want all cells to be enabled, which we can accomplish by holding Shift and left-clicking the Everything button. For now, we're going to skip talking about extra data, though we will briefly touch on it when we discuss prefab chunk streamers later in this video. Instead, let's continue by discussing LOD groups. LOD groups in S.A.M offer an alternative approach to implementing a level of detail system versus using Unity's built-in system. To determine whether you'd like to use S.A.M system, consider the trade-offs and benefits. Unity's built-in system offers a convenient way of quickly transitioning between LODs. However, all LOD versions of an asset need to be loaded at the same time, which increases memory use. Our system is more memory-friendly, as only the active LOD and the LOD being transitioned to are loaded at any given time. However, since the assets of non-active LODs must first be loaded into the scene when needed, transitions take a little bit longer to initiate. Unity's built-in system offers crossfading via shaders, usually implemented using a dithering effect. Our system offers the same crossfading out of the box. However, you can also add additional transition effects such as scaling and repositioning via coding. With Unity's system, all LOD assets must be game objects. In our system, each LOD can use different asset types. In addition, with our system, it's very easy to assign different tags, layers, and other settings to individual LOD asset chunks at runtime. Finally, Unity's system typically makes editing easier, as you can reposition and rescale a parent object and have those changes carried over to each LOD. In S.A.M, at the present moment, it is necessary to load and edit each individual LOD asset separately. Because of this, we recommend using our system for asset chunks that won't need to be changed much during the iteration process, or for asset chunks that are not compatible with Unity's built-in system, such as Unity Terrain. Another approach is to use Unity's built-in system throughout the development process, then switch to our system near the end, when changes to asset chunks are less frequent. Of course, making such a significant change to your project can affect a lot of things, so we only recommend this approach if you are aware of how it will negatively affect your project. Regardless of whether you wish to use our LOD system to support multiple LOD groups, LOD Group 1 must always be configured. Let's get started now. Each LOD group corresponds to an asset chunk group, which is simply a group of related asset chunks. In some cases, such as our example, your asset chunk group will already exist when configuring your LOD group, which makes the configuration of the LOD group relatively straightforward. In other cases, such as when using the World Designer tool to break scenes down into asset chunks, you'll need to configure your LOD group before the asset chunk group has been created. We'll discuss both scenarios when explaining the configuration steps. The group name and naming convention fields are used by chunk streamers and other tools to programmatically generate the names of your asset chunks. Using this technique means we don't need to store the name of every single asset chunk in your project, which would require a ton of memory. The naming convention field defines the format that all asset chunk names in the group must adhere to. When a naming convention asset is not provided, S.A.M automatically uses a default naming convention, which is suitable for asset chunks generated using TerraSlicer and the World Designer tool. Custom naming convention assets need only be created when using existing asset chunks that do not follow the default naming convention. The default naming convention is being shown now. As you can see, separate default conventions exists for 2D and 3D asset chunk groups, as well as for the first asset chunk in a chunk set and chunks 2, 3, 4, and so on. For all formats, %G is replaced by the group name, which will be explained in a moment. %X is replaced by the column number of the cell the chunk is associated with, and %Y the row number. For 3D formats, %Z is replaced by the layer number of the cell the chunk is associated with. When using multi-chunking, the supplemental chunk format is used, in which %C is replaced by the chunk number within the cell's asset chunk set. Any other characters besides these are literal characters and must be present in the asset chunk names exactly as shown. Note that when using multi-chunking, the first asset chunk in the set adheres to the first chunk format. All other chunks in the set adhere to the supplemental chunk format. Remember how I said %G is replaced by the group name? Well, the group name is simply the shared name that all asset chunks in the group have in common. You can think of it as an identifier for the group, something that distinguishes the asset chunks in one group from all other groups. In our example, if we examine the terrain in our group, it should be obvious what the group name is: flat terrain. Let's enter that name in the group name field. However, keep in mind that your group name will almost certainly be different. In this example, the format of the names of my terrain slices exactly match the first chunk format of the default 2D naming convention, so there's no need to provide a custom naming convention asset. If you think you may need to use a naming convention asset and are still confused on how they work, press the Confused About Naming button and the In-Editor guide will open on a helpful section that should provide clarity. Next, we need to configure the chunk type, which basically tells S.A.M which type of asset chunks are being used. In my case, I'm using Unity Terrain for this LOD group, so I'll want to set this to Unity Terrain. Doing so allows terrain neighboring to be used, which ensures there are no visible seams between terrain slices. If not using Unity Terrain, you will likely wish to use the Non-Terrain Game Object option, which covers all game objects that aren't terrain. Custom Object can be chosen if creating non-game object instances procedurally, while None can be used in special circumstances where no asset chunks are associated with the LOD group. The Use Single Chunk Set for All Cells option allows you to use the asset chunk set associated with a single streamable cell for all streamable cells for this LOD group only. If enabled, you can select the streamable cell whose asset chunk set should be used via the fields that are displayed. This option is most useful for testing purposes, so it's unlikely you will need to enable it. Use Positional Data tells SAM whether your asset chunks have position within the game world. If enabled, the asset chunks are positioned using the Chunk Manager's Set Chunk Position method, but only if the asset chunks are not already positioned correctly. Disabling this option is not usually recommended. The option is enabled automatically and cannot be disabled when using Unity terrain. The visual state of stored assets, when active option, tells SAM whether your asset chunks would be visible to the player upon activation. It is only used when the LOD group is being used with a cell visual transition controller, which is responsible for transitioning asset chunks in and out of the scene, as well as from one LOD to another. The tooltip that is displayed when hovering over this setting should give insight into which option should be chosen. Our final settings are the chunk offsets, which change depending on the axis type you have chosen. For our axis type, which is two-dimensional using XZ axes, we can specify an offset percentage for both the X and Z axes, and a raw offset value for the Y axis. If we were using a two-dimensional XY grid, we'd be able to specify offset percentages for the X and Y axes and a raw offset value for the Z axis. For three-dimensional grids, you can define unique offset percentages for all three axes. To understand how the offset values work, let's examine a sample streamable cell on a two-dimensional grid using the X and Z axes. First, it's important to note that streamable cells are always anchored at their minimum point. So when we talk about the position of a streamable cell, we are specifically talking about the position of its minimum point. For the purposes of this example, we will say that this cell is positioned at X equals 500 and Z equals 1000. We will also define the width of the cell along the X-axis as 300 and the length along the Z-axis as 200. For each axis, the offset percentage defines where along the cell's boundary its asset chunks will be placed. If you use a value of 0, the asset chunks are placed at the same position as the cell's position, at its minimum value. Increasing the value moves the asset chunks along the boundary, with 1 being the maximum value possible. In this way, the offset percentages serve as anchor points for the asset chunks. Using percentages rather than raw values allows us to utilize the same anchor location regardless of the cell's size, which, remember, can vary between different rows, columns, and layers. In this example, if we choose an X offset percentage of 0.5, the asset chunks will be placed at the halfway point along the cell's X boundary at X equals 650. If we choose 0.75 for the Z offset percentage, the asset chunks are placed at Z equals 1150. In general, most asset chunks will require anchoring at the minimum point of the cell, which means they will use offset percentages of 0. Unity terrain, for instance, will typically always be anchored at 0. Since that is what I'm using, I will set my offsets to 0. You should only need to use values other than 0 if utilizing asset chunks that are anchored at some other point. For example, if your asset chunks are Unity cubes, the anchor point would be at the center, assuming you've set your cell dimensions to be equal to the width and length of your cubes. For two-dimensional grids, there is only a single layer, so all streamable cells will have the same height. As such, there is no need to specify an offset percentage for the unused axis. Instead, you can define a raw offset value, which is simply added to the layer position of each cell in order to calculate the asset chunk's position on the unused axis. For instance, if I set a raw offset value of 150 and my world's origin is set to 0 on the y-axis, all of the terrain for this LOD group will be set to a y value of 150. Using a raw offset value gives you a little more freedom versus using an offset percentage, as you are able to position the asset chunks beyond the defined height of the streamable grid if you wish. In this video, we will not be discussing multi-chunking further, though you should have a general understanding of how it works based on our earlier discussion of asset chunks. If you wish to learn more, you can navigate to the multi-chunking window and press the What is multi-chunking button. Now that our streamable grid is set up, we can start setting up our scene to enable streaming using S.A.M. The easiest way to do this is to use the Asset Menu command, found in Game Object. Create Other. Deep Space Labs. S.A.M. Default S.A.M setup. This command adds several game objects and components to the scene. Component Manager, World, and Active Grid are all game objects containing a single component of the same name. Each scene is only allowed to contain a single component manager. However, you are free to make use of multiple worlds and active grids if needed. While the component manager and at least one world are required, the active grid is technically an optional component. However, for most users, it will make sense to keep it in the scene. Default Components contains components which have alternative versions or which can be customized using custom implementations, while other components currently only contains a boundary monitor component, which is used in conjunction with active grids to track the player. When using this menu command, some references between the different components are configured automatically. Please bear in mind that if you remove, add, or change out components, you will need to manually assign the new components to the appropriate fields on other components. For example, if you decide to use a different execution controller, you will need to assign the new one to the execution controller field of the world, which can be found within the optional components window. Now let's briefly go over all of these components one by one, starting with the Component Manager. The Component Manager manages worlds and active grids to make certain operations easier. For instance, when you wish to initialize S.A.M, rather than initializing each active grid and world in your scene individually, you can initialize the Component Manager and it will take care of all of the hard work for you. It also carries out save and load operations and can be used to create and destroy worlds and active grids at runtime. The Component Manager ID is an integer value that should be unique for each component manager in your project, although it should be noted that most projects will typically only have a single component manager. At this time, we're going to ignore the rest of the settings on the component manager and focus solely on its initialization. The component manager can be initialized over 2 frames or in a gradual manner that is more performant. 2-frame initialization is generally only suitable for testing purposes, as it takes up a significant amount of frame time, and the player will notice a lag spike. Gradual initialization limits the amount of frame time used, but is carried out over multiple frames. While it takes longer to complete, its progress is tracked so that you can display a loading screen with progress bar. As such, it is more suitable for use in an actual game. The Initialize on Awake option, when enabled, forces the component manager to automatically perform 2-frame initialization when the scene is loaded, which will be carried out in the awake and start methods. If you disable this option, you can manually trigger 2-frame or gradual initialization using a method call, or using the Inspector Context menu if in the editor. The latter is intended for testing purposes only, as it is not usable in an actual game. For the former option, in order to call the appropriate method, you will need to write a custom script with a reference to the component manager. It should also be noted that the gradual initialization method is called like a coroutine. For help with these methods, as well as help with other ways to interact with S.A.M through scripting, please visit the API on our website, a link for which has been provided in the description of this video. Chunk managers make decisions about whether asset chunks should be pooled or not, and manage the pooling behavior if it is used. They also handle some asset chunk-specific operations, such as getting and setting position data. By default, a non-pooling chunk manager is added to the scene. If you wish to use a pooling manager, you can add it using the Add Component menu. Each manager contains a helpful section in the guide, which will help you decide whether it's suitable for your project. Custom chunk managers can also be created via scripting to support custom pooling solutions or custom asset types. You can assign chunk managers on a per LOD basis, so you are not confined to using or not using pooling for the entirety of your game world. That is to say, you can make pooling decisions based on the type of asset chunks being used by each LOD group or world grouping if you wish. Chunk streamers are responsible for streaming new asset chunks into the scene and removing them when they are no longer needed. Using scenes for your asset chunks is generally more efficient than using prefabs, so by default, we add a scene chunk streamer to the scene. This component streams scenes that have been added to your build settings. With that said, it is also common to use prefabs for your asset chunks, as we are doing in this example for our terrain. If you know that you are not going to make use of the scene chunk streamer, you can remove it and replace it with the chunk streamer you wish to use using the Add Component menu. By default, S.A.M includes chunk streamers for streaming scenes and prefabs, as well as addressable versions of prefabs and scenes. Addressable assets offer the greatest flexibility but are the most difficult to work with. You can also create custom chunk streamers via scripting to replace our default streamers or to support custom asset types. In our example, we need to add a prefab chunk streamer to load in our terrain prefabs, but there's a chance we might use the scene chunk streamer in the future. So rather than remove it, we will create a new game object and add the prefab chunk streamer there. When using multiple components of the same base type, we recommend placing them on separate game objects, as it will make assigning the components to fields on other components easier. Speaking of assigning the components, we should do that now, otherwise our new prefab chunk streamer will not be used. There are several ways to assign this streamer. However, for now we will simply assign it to the default chunk streamer field in the world's overridable settings window. If you stuck with the scene chunk streamer, the default settings should be suitable for most users, though you are of course free to explore them more and modify what you want. The same goes for the prefab chunk streamer, with one exception. If your prefabs are stored directly in a folder called Resources, no additional setup is required. If, however, the prefabs are nested in one or more subfolders, the Prepend Extra User Data option must be enabled. Now, when loading prefabs, the streamer will prepend a subfolder path to the prefab load keys, allowing them to be loaded from the nested folder. Of course, it doesn't know which subfolder path to use by default, so we need to provide it that information. We can do this via the Streamable Grid. If all of your LOD groups use prefabs stored in the same nested folder, this next step can be done via the Global Extra Data window. If your LOD groups have their prefabs stored in separate nested folders, however, you'll need to modify the LOD group specific extra data for each group that uses prefab asset chunks. To add the nested folder path data to the Streamable Grid, select the nested folder where your prefabs are stored on the left side of the project hierarchy, and then press the Copy Folder button on your Streamable Grid. Once the nested folder is displayed, press the Add Entry button. Now the prefab chunk streamer is ready to load the prefabs from this LOD group. You may be wondering why we didn't just add the nested subfolder path to the streamer itself. While this is a functional strategy, doing so would limit the prefab chunk streamer to only being usable with LOD groups, whose prefabs are stored in that particular subfolder. The extra data technique we are using allows the streamer to be used with multiple LOD groups, whose prefabs are stored in different subfolders within the Resources folder. Execution controllers can be used by the worlds to maximize or limit the amount of frame time they use. By default, a frame rate-dependent execution controller has been added to the scene. This controller stops the world from starting or continuing execution within a frame if that frame has already taken up a set amount of time. There are 2 additional default execution controllers available for use, which you can add using the Add Component menu. You can also create custom execution controllers via scripting. Note that execution controllers are not absolute. The world's execution within a frame can be less than or greater than the expected time in several scenarios. If you are interested in execution controllers, we encourage you to read the dedicated chapter on them in the in-editor guide. The boundary monitor is responsible for monitoring cell boundaries in order to determine when a player has crossed from one cell into another. It is solely used in combination with active grids, so if you stop using active grids in the future, you can safely remove this component as well. The detection frequency is the default frequency at which the boundary monitor will check the player's position to see if they've crossed a boundary. The value you choose will depend on the speed that your player moves and the size of your streamable cells, with faster players and smaller cell sizes requiring smaller values. While you can use multiple unique boundary monitors if using multiple active grids, typically only a single boundary monitor is needed, regardless of the number of active grids in use. This is because active grids contain options for overriding the default detection frequency of the boundary monitor on a per-streamable grid basis, allowing a single boundary monitor to be used with different grids of varying cell sizes. Worlds are the most important components in the Streamable Assets Manager toolkit. They are the physical manifestations of streamable grids, taking the grid's data and combining it with their own data to produce a virtual game world in tangible scene space. The configuration of the world also enables the use of the World Designer tool, which offers powerful editing capabilities for iterating on your world and creating asset chunks to be used by your world. In most games, a single world will suffice. However, you are free to make use of as many worlds as you wish, though you need to ensure each world uses a unique world ID. You can also create and destroy worlds at runtime using the robust API. The world contains a ton of settings, but for now we'll focus on configuring only those settings that are necessary to get your game up and running. Feel free to explore the dedicated world chapter to learn all that this crucial component has to offer. In the General Settings window, the only settings you may need to adjust at this time are the Endless World settings. These options allow you to make one or more of the world's axes endless, which will cause the axes to repeat in both the positive and negative directions to simulate a spherical world. You can find more detailed information in the Endless or Fixed section within the Worlds chapter of the In-Editor Guide. Let's skip the Origin settings for the moment and move ahead to the Optional Components window, which contains only 2 fields for an execution controller and hierarchy organizer. We have already briefly discussed execution controllers, and one should be assigned, so let's skip that. Hierarchy organizers allow you to organize the asset chunks loaded in by chunk streamers within the scene hierarchy. When one is not provided, all asset chunks are loaded in as root game objects, either in the scene the asset chunk is loaded in on or in the main scene the world is contained in. This can be problematic for several reasons, the most notable being that it slows down searches involving the scene's root objects. It can also make navigating and finding asset chunks within the scene hierarchy difficult, both visually within the editor and with scripting. For now, you can leave this field blank. However, we recommend reading more about hierarchy organizers by pressing the question mark button next to this field. The Overridable Settings window contains settings that are applied to all world groupings and LOD groups by default, but which can be overridden on a per world grouping basis, and in many cases on a per LOD group basis. You should attempt to set these settings to values that will work with a majority of your world groupings and LOD groups if possible. This will reduce the number of settings that need to be overridden. With that said, don't worry too much about getting these settings exactly right, as it can be hard to predict what's needed at this stage. Moving on to groupings, the world contains a single world grouping by default, which serves as the base grouping. You can add more which will serve as subgroupings, but for now, a single grouping should suffice. Each grouping corresponds to a single streamable grid asset and is intended to represent a different aspect of your world. For example, trees could be on one grouping, terrain on another, buildings on a third, and so on. At this time, you should assign the streamable grid asset you created earlier to the grouping, to the streamable grid field, which can be found in the General Settings window of World Grouping 1 Settings. If you add more groupings later, remember these 2 things. First, subgroupings must always be compatible with the base grouping, meaning the axes types must be compatible and the size of each used axis must be equal to the base grouping's corresponding axis. Second, groupings are loaded in order, with the base grouping loaded first, then grouping 2, grouping 3, and so on. They are unloaded in reverse order. This allows you to support dependencies between groupings. For instance, physics-based objects on a subgrouping can be guaranteed to load after the ground terrain that they sit on, which ensures they do not fall through the world. More information can be found in the World Grouping section within the Worlds chapter. Cell Visual Transition Controllers can be assigned via the Optional Components menu. These powerful components allow you to control how asset chunks are transitioned in and out of the scene, as well as from one LOD to another. World grouping listeners work similar to event listeners, allowing you to hook into the world update process to perform custom logic on world groupings or world cells at key moments in the update cycle. They are especially useful for adding third-party tool integrations. For the moment, however, we can skip adding any. The World Designer window is where you will launch the World Designer tool, which allows you to perform a variety of actions related to this world. You can explore the World Designer chapter or dedicated tutorial videos on this incredible tool to find out more information. Now let's return to the Origin Settings window. The Origin Cell and Origin Position settings work in tandem to define the position of all cells, and thus asset chunks, on the world. How you set these values will depend on whether you plan on using a fixed or floating origin world, so let's briefly discuss their differences. In a fixed world, world cells and asset chunks are loaded in at fixed positions and are never moved. The worlds must be smaller to avoid floating point issues, however they come with benefits as asset chunks can be marked as static, allowing them to be used with build time, static batching, and other static-dependent workflows. Floating origin worlds attempt to avoid floating point issues by periodically changing which world cell is the origin cell. When the origin cell is changed, that cell is shifted, so its position becomes the origin position, and all other loaded world cells are also shifted, which effectively keeps everything close to the origin position. However, since asset chunks need to be moved at runtime, they cannot be marked as static and lose all benefits of that status. The origin position serves as the reference point for all cells and asset chunks associated with the world, which can be thought of as the point around which the world is loaded. The origin cell is the world cell from the base grouping that is placed at the origin position. All other cells are placed in relation to it. When using fixed worlds, we recommend keeping the origin cell set to 1, 1, 1 and modifying the origin position such that the entire world will be centered around 0, 0, 0. To do this, you should calculate the size of each used axis from the base grouping's streamable grid and divide by 2. Then set the origin position on each axis to the negative of this value. For example, in my terrain grid, I am using 8 rows and 8 columns, with each cell having a length and width of 125. The total length and width of my streamable grid is 1,000. Dividing that by 2 gives me 500, so I can set my origin on the X and Z axis to minus 500. The height of my layer is 208, half of which is 104, so I can also set my Y origin to minus 104. For floating origin worlds, while using 0, 0, 0 for the origin position may seem like the obvious choice, in actuality, a negative origin position is typically better. This is because streamable cells are anchored at their minimum point. If you use 0, 0, 0 as the origin position, it will usually result in more of the world being placed on the positive axis versus the negative, which is not ideal. Instead, you can use the average dimensions of a cell on your base grouping streamable grid to offset the position. Simply divide the average dimension on each axis by 2, then use the negative of those values as the origin position. You should also set the origin cell to the cell which the player will start in, which will ensure the starting asset chunks will be centered around 0, 0, 0. For setting the origin position, you can either use the position of the game object the world is placed on, adjusting it as needed, or you can uncheck the option seen here, which allows you to manually enter a position. The origin cell change strategy dictates how the origin is changed for floating origin worlds. By default, it is set to duplicate world, as this option requires no additional setup. However, we recommend changing it to shift world in the future if you are serious about using a floating origin world, as it is more performant and uses less memory. You can use the standard world shifter as the world shifter by adding it via the Add Component menu, or you can create a custom world shifter for extremely fine-tuned control over how the world is shifted during origin cell changes. If using a floating origin world and an active grid, you will likely wish to enable the Allow Active Grid Recentering option as well. This allows an active grid synced to this world to track its player, and when the player crosses a pre-configured boundary, to automatically trigger an origin cell change. Note that the values set represent distances from the origin, not raw position values. As such, all values must be positive. Also note that some additional setup on the active grid is required for auto-recentering to work, which we will talk about shortly. The world provides a comprehensive framework that defines which cells and asset chunks can be loaded. In addition, it manages those cells and asset chunks as well as the operations required to load, store, and unload them. But how do we decide which cells should be loaded? While there is a mechanism to do this purely via the world component by means of world regions, typically the decisions about what should be loaded and unloaded is under the umbrella of another component known as the active grid. The active grid component tracks the position of a single-player object and then uses that position in conjunction with loading blueprints to make decisions about which cells need to be loaded and unloaded. You can use a single active grid or multiple active grids to support local multiplayer games. Unlike the world, the active grid is an optional component. However, if you do not use it, you will need to use world regions or a custom script in order to tell the world what should be loaded. As such, most developers will wish to make use of at least one active grid. Despite its name, the active grid can consist of multiple grids of active cells, with each grid representing a grouping. Each grouping corresponds to the same numbered grouping on whatever world the active grid is synced to. For instance, grouping 1 on the active grid corresponds to world grouping 1, while grouping 2 corresponds to world grouping 2, and so on. It should be noted, however, that it is perfectly valid for the active grid to have more or less groupings than the world it is synced to. This allows the active grid to be synced to different worlds with differing numbers of groupings throughout the course of the game, if necessary. The default world the active grid starts synced to has already been set. The same goes for the boundary monitor, which is responsible for tracking whether the player crosses cell-aligned or world recentering boundaries. At this point, you should assign the player the active grid will track. In most cases, this player will be a normal Unity game object, and the position of the player will be determined by its transform component. If this is the case for your game, you can assign the player to the player transform field, making sure the transform that is assigned is the transform that accurately represents your player's position within the game world. If your player does not fit this description, you should open the In-Editor Guide to the General Settings section of the Active Grids chapter. There, you will find a subsection detailing the player field and the various options you have available to you regarding it. If you are using a floating origin world, you will want to leave the Allow Grid to Recenter world option enabled. With this option enabled, the active grid will register the world recentering boundary defined on the world component with the boundary monitor. When the player crosses the boundary, a world origin cell change will be initiated automatically by the active grid. If your world's origin change strategy is set to duplicate world, we usually recommend enabling the Move Player After Origin Cell Change option, which ensures the player is shifted with the world. If using a world shifter, we recommend disabling this option, as it is usually better to let the world shifter shift the player. The Align Player to Terrain option is useful if you are using terrain. With it, you can change the player's X and Z position in the scene, and upon playing your game, the Y position of the player will be set based on the height of the terrain at that X and Z position. When enabled, you just need to tell the active grid which grouping is using the terrain. You can also bump the player up or down by a fixed amount, which is useful if your player's position is not quite at the same level as the part of the model that will sit on the terrain. Last but not least, we need to assign the loading blueprint that will be used by our world grouping. However, if you navigate to the Groupings tab, you will notice that it is currently not possible to do so, as a loading blueprint repository has not been assigned to the active grid. We can rectify this by creating a loading blueprint repository asset, which is accomplished by right-clicking the folder where we want to store it and selecting Create Deep Space Labs, S.A.M, Loading Blueprint Repository. It is recommended to give this repository asset a new name to differentiate it with other repositories you may create in the future. Each repository can hold one or more loading blueprints, though by default it is empty. To create a loading blueprint, click on the repository and then press the Edit Repository button. This will open the Loading Blueprint editor. Now, press the Create Loading Blueprint button to create your first blueprint. A loading blueprint contains one or more loading patterns, which in general consist of inner area and non-inner area cells. Inner area cells, shown here in blue, represent a travel-safe region. So long as the player stays within this region, nothing on the active grid grouping that uses this blueprint will change. Once the player crosses the inner area boundary, however, the loading pattern is changed depending on the type of blueprint in use. You can read more about the type of loading blueprints available by hovering over the blueprint type label, or by opening the dedicated Loading Blueprints chapter within the In-Editor Guide. For now, the default 2D uniform ring pattern is sufficient. However, you may wish to give it a new name so that you can identify it more easily in the future. Once done, we can close the editor, then assign the asset to the active grid, either by dragging and dropping it or by using the Object Picker menu. If we navigate to our grouping one now, we can see that it has already been assigned the blueprint we just created, since that is the only blueprint in the repository. If we had more blueprints, we could use the drop-down button here to select the blueprint we wanted to use. It should also be noted that you can change the blueprint a grouping uses at runtime, and those changes will persist across game sessions through the use of save data. This can be useful, amongst other things, to dynamically adjust view distances based on player configurable settings. There are more settings on the active grid that you can play around with, but for now, that should be enough to allow you to enter play mode and test your game. When you enter play mode, if you have the Align Player to Terrain option enabled, you may notice the player bouncing up slightly. This is usually due to the player intersecting the terrain and the physics engine kicking it out to resolve the intersection. We can rectify this issue by exiting play mode and adjusting the Y offset value on the active grid so that the player does not start intersected with the terrain. In this case, I have predetermined that a value of 1.4 will work nicely. However, you may need to experiment to find the best value for your player. Upon re-entering play mode, the bounce has been removed. If we examine the terrains that have been loaded, we can see that the center cell, which is the cell the player's initial position is in, is cell 5-5. An additional ring of cells has been loaded around this cell, which mimics the loading blueprint we created earlier. If we move the player to the west, the player crosses over the inner area boundary, which triggers an update of the active grid. This causes cells and asset chunks to be loaded and unloaded, effectively shifting the world to the west. My scene is running nicely. However, I don't really like where my player is starting. There are a few ways I can solve this issue. However, the best option is to use the World Designer tool to load the terrain pieces in the editor, which will allow me to position the player exactly where I want. To use the tool, I'll exit play mode and navigate to the World Designer tab of the World component. To launch the tool, I first need to create a World Designer data asset, which holds editor-specific data like editor world regions and view settings. By default, this data asset is not bound to the world, which keeps the scene clean of changes. This is important in team-based workflows that use version control, as it allows each team member to use the World Designer tool to load and edit different parts of the world without modifying the main scene. You can read more about this, as well as the World Designer data asset in general, in the World Designer tool chapter of the In-Editor guide. Binding is always recommended for solo developers, so for now, I will choose to do so. In order to launch the World Designer tool, the scene the world is located in must not be in a dirty state. However, binding data to the world makes the scene dirty, so I will need to save the scene in order to launch the tool. Fortunately, there is a handy button included in the World Designer tab that makes doing this easy. After, I can launch the World Designer tool by choosing a world grouping which will be its initial focus. For now, I only have a single world grouping on this world, so there is no choice to be made. The World Designer tool has a ton of features and uses. However, for now, we will only worry about one of its main uses, loading asset chunks associated with our world. I can choose to load all cells, or just a small subset. For this example, I'll just load a subset of cells near my player's current location at 000. Remember, however, that in this example scene, I have set the origin of my world to -500 on both the X and Z axes. Therefore, if I select cell 11, I can see that its position is not close to my player at 000. By highlighting the cells in the World Designer tool, I can see the real-world position and boundaries of those cells within the scene, which is handy for figuring out which cells I want to load. I'll load the 4 cells surrounding the player's current position now. Then, I'll reposition my player to the new location that I want. At this point, I can enter play mode, and the world component will automatically unload any asset chunks associated with it. This is an editor convenience feature. When building your game, you should make sure to manually unload asset chunks using the World Designer tool before building it. Also note that this convenience feature will likely result in it taking longer to enter play mode, so in some cases it can be better to manually unload the asset chunks first. Upon exiting play mode, the player's position and other data is lost, as saving is not configured by default. If you wish for data to persist between game sessions, you can take a look at the Saving and Loading Data section of the Component Managers chapter within the guide, which serves as a jumping-off point for understanding these systems. With this video, you should have a general understanding of how to set up S.A.M. You can continue adding world groupings, either by using the World Designer tool to break down existing scenes into streamable asset chunks, or by creating streamable grids for asset chunks that you have already created. Feel free to explore the many different components and features of S.A.M. by making use of the tooltips and question mark buttons found in the inspectors, and by referencing the In-Editor guide whenever a more detailed explanation is required. We look forward to seeing the wonderful and complex worlds your imagination brings to life using S.A.M, the Streamable Assets Manager.